Today I'm going to explain exact ordinary differential equation. Now, what is exact ordinary differential equation? By the definition on the board, an exact ordinary differential equation is formed by directly differentiating its primitive without any other process. Meaning, if you are given a differential equation of this form, m ds plus n dy equals 0, this differential equation is said to be exact if partial differentiation of m with respect to y is equal to partial differentiation of n with respect to s. Now, if you are given a differential equation in such a way that you can differentiate m partially with respect to y and differentiate n partially with respect to s, if the both partial differentiation is equal, then we say the differential equation is exact. Now, how do we solve problem related to exact ordinary differential equation? Now, let's solve this example. Now, in example 1, we are given this differential equation. Now, how do we go about it? The first value you have here is denoted as what? As our m ds, because of this. So the whole of this is m, and the whole of this is n. So we have m ds and we have this to be n dy. Now, let's show if this differential equation is exact or not. Now, by applying the partial differentiation of m with respect to y to be equal to partial differentiation of n with respect to s. Now, what's the value of our m? Our m equals, let's differentiate this with respect to y. So there is no y variable here, so this is not differentiable. Now, if you look at this, we have 3x squared y squared. Now, if you differentiate this with respect to y, we have 6x squared y minus, if you differentiate this, you have 6xy squared. So that's, we've differentiated m with respect to y. So differentiating m partially with respect to y, we have this. And when we are talking about partial differentiation, we are only concerned about the variables we are differentiating on, not the other. Like in this case, we are differentiating partially with respect to y. So that's why I'm differentiating y alone. Here, y alone. So if you differentiate this, you know from the definition of our integration, when you have y raised to power n, is n x n y n minus 1. So that is the procedure, or that is the method I used here. So differentiating this, so we have our partial m with partial y to be equal to this value. Now, let's look at partial n with respect to s. Partial n with respect to s. Now, let's differentiate this now, the old value here with respect to s. Now, we have s here. If you differentiate this, we have what? 6s squared y. And if you differentiate this as well, we have minus 6sy squared. But because there is no s here, it is of no use. Now, from the partial differentiation of m with respect to y, partial differentiation of n with respect to s, you can see that the two solution is equal. So in that case, we say our partial m with respect to partial y equals partial n all over partial x is what? Is exact. So partial m with respect to y and partial n with respect to s is what? Is exact, because the values are equal. Now, since we can ascertain that this differential equation is exact, the next thing to get our solution is to integrate value of m with respect to s plus integrate n without without y must be equal to 0. Let me explain this. Anytime you are solving problem related to exactness, immediately you notice that the value are exact. The next thing is to get your solution, your answer. And how do we get our answer? You integrate m with respect to s. And you integrate n without s. You integrate n without s, meaning that any value you see here in the right hand side where n is with s will be neglected. Now let's look at this. Now, since the value here is exact, now let's integrate the whole of this with respect to s. If we integrate this with respect to s, integration. Now let's integrate this. If we integrate 5x raised to power 4, this is a constant. You have 5 integral of x4. Now, if we integrate this, you have 5 x5 all over 5. So 5 will cancel 5. We are left with x5. Now, go to the next one. Let's integrate 3x squared y squared. Don't forget, we are integrating with s. So this will give us, let me do it in, let me be explicit in my explanation. Now, let's integrate this. If we integrate this, we have 5x5 all over 5. Plus, if we integrate this, we have 3x raised to power 3 all over 3 y squared. Y is constant in this case. Now, if we integrate this with respect to s, we have what? Minus, because of this minus, 2x squared all over 2y cubed. So at the end of the day, 5 will cancel out 5, 3 will cancel out 3, 2 will cancel out 2. We are left with x raised to power 5 plus x cubed y squared minus x squared y cubed. So that's the value of the integral of m ds. So we got s raised to power 5 plus x cubed y squared minus x squared y cubed plus, let's integrate n now. We integrate n with respect to what? With respect to y. Now this is very straightforward. I said integral of n without s. That means any variable you see here with s will be nullified. So we have s here, so we won't integrate this. We have s here, we won't integrate this. We are only left with minus 5y raised to power 4. So we have minus 5y raised to power 4. So that's why I said n without s. N without s. So because there is s here, there is s here, they are of no use. So we are integrating minus 5 raised to power what? 4. Now if we integrate this, the integral of this will give us minus 5 integral of y raised to power 4. That will give us what? Minus 5 y raised to power 5 all over 5. So 5 will cancel out 5. We are left with minus y raised to power 5. So the whole of this, because of the negative sign, which will affect this, then we have minus y raised to power 5 equals c. Equals c, where c is the constant. So this is our final answer. So when you are solving problem related to exactness, the first thing you are going to do is to determine if it is exact or not. After you have confirmed that differential equation is exact, now the next thing is to integrate m with respect to s and integrate n without s. So our final answer is this. So I'll solve more problem on this. Thank you. Let's solve this second example on exactness. So we have similar question on the board. So we denote this as our m. So our m ds will be equal, the first one is our m, and that will give us s plus y minus 10. So the second one here is our n. So our n dy will be equal to what? S minus y minus 2. Now let's show that this 2 is exact or not. Now, so let's find our partial m over partial y. So let's differentiate this with respect to m. Partial differentiation, don't forget. Now with respect to y, we have what? 1. Because we are not meant to differentiate s. Partial differentiation. So this is not there. If you differentiate y here, you have 1, and this is a constant. Now let's look at our partial n with respect to s. Now we are differentiating this partially with respect to s. Here, if you differentiate s, you have 1. So these two are constant. So now if you look at this, our partial m now with y is equal to what? Partial n with respect to what? Partial s, which is equal to 1. So we can say that this differential equation 1 is what? Is exact. And if it's exact, how do we get our answer? We have the integral of m ds plus integral of n without s. Meaning you integrate m with respect to s in equation 1. And here you integrate n as well without s. Now let's integrate m with respect to s. If we integrate this, you have what? S squared all over 2. So I try to integrate this. And if you look at integrate s ds plus integrate y ds minus integrate 10 ds. That's the meaning of this. Now if you integrate s, you have x squared all over 2 plus y is a constant because we are integrating with respect to s, but we have y here, so y is a constant. So we have something like this, y integral ds. So if we write y and integrate ds, you have s minus the same thing. Since we are integrating with respect to s, here y is constant and 10 is also constant, so this is 10s. So at the end of the day, the whole of this will give us x squared over 2 plus sy minus 10s. So that is, we've integrated this with respect to s. Now the next one is integrate n without s. Now we have s here, so we are not integrating this. Thank God we have y here. So if we are integrating this, let me simplify it further. If you look at this, it's the same as integrate s. We are not integrating this, as I said earlier. So we are left with this. Integrate minus y dy minus integrate 2 dy. So we are going to have minus y2 all over 2 minus 2y. So at the end of the day, we are able to get this. So the whole of this will now be minus y squared all over 2 minus 2y. So this is our answer. So I will write it here. So x squared plus sy minus 10s plus, what's the value of our y after integration? We have, so this minus will affect. This minus will affect the plus. So we have minus y squared all over 2 minus 2y all equals c. Where c is our what? C is our constants. Thank you. Now, this is another example on exactness. Similar procedure. We have our m to be equal to y sec square s plus sec s tan s. So we differentiate m partially with respect to what? With respect to y. So partial m with respect to y. Now let's differentiate this with respect to what? With respect to y. Now this is y here. So if you differentiate y, you have 1. So we are left with sec square s. So this one does not contain any variable y, so it's of no use. Now let's look at our n. Our n equals tan s plus 2y. So we now differentiate n partially with respect to what? With respect to s. Now if you differentiate tan x, you have sec square s. Now we can confirm from this that our partial m with respect to partial y is equal to partial n with respect to s, because we got both sec square s and sec square s. So partial m partial y equals partial n partial s. So we can say the differential equation in what is exact. The is what? Exact. Now, if it's exact, the next step is to find our solution. And what's our solution? Our solution is integrate m with respect to s plus integrate n without s equals c, where c is constant. Now, let's integrate this with respect to s. Now, if we integrate this with respect to s, now, if we integrate, let me explain this. You integrate y sec square s. So y will be what? Y will be constant. Since y is constant, you have y integral of sec square s. So if we integrate sec square s, you have what? Tan s. Don't forget that integration is what? Is the opposite of differentiation. So you have y tan s for this. So y tan s plus, now let's integrate this with respect to what? With respect to s. Now if we integrate sec s tan s, we have sec s. So the whole of this will now give us y tan s plus sec s plus, now let's integrate n without s. Now the whole of this is n and the whole of this is m. Now integrating this n without s, that means we are integrating all the variables or values inside this bracket without s. Now tan s here contain s, so we are not integrating this. We are only integrating what? 2y. And if we integrate 2y, we have 2 is constant, integral of y, all the y. So 2 is y raised to power 2 all over 2. So 2 we cancel out 2. We are left with y squared. So integrating this without s, then we have the whole of this to be what? Y squared. All equals c. So this is our final answer. So after integrating this, we got y tan s plus sec s. And after integrating n without s, we got y squared equals c, where c is constant. Thank you. This is another example under exactness of differential equation. Now we have this example on the board. The first value here is our m ds, and the second one is what? Our n dy. So what's our m? Our m, 2xy plus ey, and our n is what? S squared plus s exponential raised to power y. Now let's differentiate our partial m with respect to partial y. Our value here, if you differentiate m, if you differentiate this with respect to y, we have what? 2s. Because if you differentiate this, you have 2s. With respect to y, 2s. Now, if you differentiate exponential raised to power y, we are still going to have the same thing, exponential ey. So that's our value for partial m with respect to what? Partial y. 2s plus exponential raised to power what? Y. And for the second one, partial differentiation of n to what? To s. Now if you differentiate x squared, we have 2s. And if you differentiate this with respect to s, we have what? We have exponential raised to power y. Because if you differentiate with respect to s raised to power 1, this will be 1x, 1 minus 1, 1x, 1 minus 1 is 0, s raised to power 0 is 1, so we have 1. So if the whole of this is 1, we are left with exponential raised to power y. Now from the rule of exactness, we can say that our partial m to partial y is equal to partial n with partial s. So we can say this differential equation 1 is exact. Now, after getting the fact that partial m with respect to y equals to partial n with respect to s is exact, and the next thing is to get our solution. And what's our solution? Our solution remains integral of m ds plus integral of n without s. Now, so let's integrate this with respect to s. Now, if we integrate this with respect to s, we are going to have 2x squared all over 2y. Plus, if we integrate this with respect to s, we are going to have our s e y. So the whole of this gives s squared y plus s exponential what? ey. Plus, now let's integrate n without s. Now, if you look at this differential equation very well, we have s here and we have s here. So it is nullified. We don't have the value. You can only integrate n if there is no s. But because we have s, it cannot be integrated. So the whole of this will be 0. So our answer is x squared y plus s exponential raised by y equals c. So that's our final answer. I hope you understand what exactness is. In the next class, I'm going to solve reducible equation to exactness, where we'll be talking about partial m minus partial n all over n. We'll be talking about the second case where we have partial n minus partial m over y all over m. And that can only occur if and only if it is what is a function of y. And we also have the homogeneous condition. We also have the condition of sy and so on. So in the next class, I'm going to talk about a reducible equation to exactness, which implies that there are some differential equations that are not exact. So what are we going to do to make such differential equation to be exact? Now, that is when we use the different cases that we have to solve them. So in the next class, we are going to talk more about reducible differential equation, and you are going to enjoy the class. Thank you.